Okay, good afternoon. So let us now start another part of this chapter that was left. And that is an important part. So that is called volumes of revolution. So we want to calculate volumes of solid objects somehow. But to motivate you is this. For example, you have a function whose graph is given to you. Of course, there is no volume involved yet, because for having a volume, you have to have a 3D solid object, and then you can ask what the volume is, yes? But let us say that I have a function, and then I limit myself on the interval from a to b. And then, of course, you know that you have an area there. If I want to calculate the area, you know what to do. So it becomes what? Integral from a to b f of x dx. Yes? But now the point of the volumes of revolution is that, let us say that I want to rotate this area, or I would say this function, the curve, about the x-axis. If I start rotating that, it will generate a solid object, a three-dimensional object. Yes? We want to be able to find the volume of that generated object. Okay, so that is, if I rotate this, the solid 3D object that I get is called the solid of revolution. You revolve it and you get an object. You want to find the volume of that object. For example, I don't know if I can draw it. It's not that easy to draw it, but you know what happens more or less. So let me try to give you a flavor. If I can draw it, something like that. And then what you do, you start rotating it, you know. Might be that's a good representation. So you can feel what I'm saying. That's, I want to find the volume of that object. Is the idea clear? Okay. But before doing that, let me go back and look at the volume in a little bit different way. Area in a different way. So this is the one I want you to learn, okay, because that's very important. So if I give you this function, f of x, and then I want to find the area. So back to the old discussion yet. I want to find the area, but I want to look at it a little bit more practical way. So what you do, you concentrate on a very small thickness, which of this, for example, I don't know, I don't want you to draw a rectangle for you, but let us assume that the thickness of my pen is generating for you a very narrow rectangle. Okay. Of course, I call it rectangle, but it is not essentially a rectangle. Why? Because of one problem. Because rectangle has 4 sides, but all sides are straight line segments. Yes? So here, the border on the left, I intentionally want to draw it narrow. I don't want to draw it like that. Of course I can, but I want you to understand this is the mentality I want you to develop if you want to be good in integral calculus. So let me just draw this. Imagine this, not imagine, this is really a thin rectangular shape. But it is not exactly rectangle, because even though this line, the left border is a straight line, the right border is still a straight line, the border below is also a straight line, but the border above is a curve. But it is very, very narrow. Yes? So it is not exactly rectangle, but it is close to a rectangle. Okay. Now, what you do, I would say, okay, let us say that this point has x coordinate x. Okay? By changing x, what happens? These narrow blue rectangles start moving, sweeping this area. Yes? If I ask you, can you tell me what is the height here? What is the height if this is x? The height is f of x. And this very small thickness, I call it dx. You remember I told you for the time being dx doesn't have any very particular meaning for you. But let us now change that perspective. And I would say dx is a very small variation in x. So it is a length again, but a very, very small length. Yes? Now, I ask you, what if you imagine that this blue thing that you see here is indeed a rectangle? What is the area of this rectangle? The area of this rectangle is the height, f of x, multiplied by the width, yes, which is d of x. What you get is called an infinitesimal. It's a very small number, not because f of x is a small, because d of x is very, very small. Even d of x that you see here is an exaggeration. dx even is smaller than that. That's also an infinitesimal. But the miracle here is that this is not zero. It's a very, very small number. But then I would say that what is this? I would say this is an area of this rectangle, but this rectangle, I call it d of a. This is a very small area. Okay, so here, this has a meaning now for you. D of a means the small area that you see here is equal f of x dx. Of course, there is an approximation going on, but that approximation becomes equality when dx becomes smaller and smaller and smaller. So what you write a small area is equal to f of x dx. But naturally, what you want to do, if you want to find the total area, what do? You add them up, okay? If you want to add finite numbers, you use sigma to add them up. If you have discrete number of them, for example, if you have 1 million terms, you want to add them up, you use sigma. If you have 1 billion terms, if you want to add them up, you use sigma. But if you have infinitely many terms and still you insist to add them up, sigma is useless because sigma has a counter which goes up with discrete values. But here you have a continuum. Okay, so in this case, you want, because this is not useful for you, you want to add these areas to find the total area on the one hand. On the other hand, you know that you are working with infinitesimals. I have infinitely many of them. So if I want to find the area, the sum, which I usually use sigma, turns into an integral. So integral, this means a stretched s for sum. But my x starts from a and goes up to b. So this is a to b. So this idea I want you to have to back of your head, because whenever you have an infinitesimal number and you realize you want to add up the infinitesimals to get your quantity that you are interested in, you need to remind yourself about integral. So sigma is addition. Integral from a to b is also an addition. Yes? But this is adding finitely many terms. This is adding infinitely many small infinitesimal terms. I want you to have this in the back of your head. Okay, now I want to use the same idea. Then you see that finding a formula for the volume is extremely simple if you can develop this idea. Okay, so first of all, let me make sure that you understand these things. So can you say what happens if I have this bit of horizontal straight line? Yes. So let me call this H. This is a horizontal line segment. And let us say that, for example, from here to here, I call it R. This distance is R. Okay, now imagine in your head, I take this straight line, this bit of a straight line, and rotate it about the x-axis without changing these distances R. Can you imagine what will be the solid object generated by this act? Yes?
A cylinder.
It's a cylinder. Yes? I hope that it is easy, understandable. Yes? So you get a cylinder. If you look at the formula sheet, the volume of the cylinder is pi, the radius squared multiplied by the height. Can you imagine now, if you do this cylinder, which one of these parameters you see will play the role of the height? Exactly the one that I called h. This becomes the thickness of this cylinder. Do you see that? Yes, Afsha? Is that okay? Okay, my picture is awful, I know, but so let me make it a little bit better because I thought that it might be very trivial. So if you just draw that, then it becomes a cylinder, yes? So, so how should I draw it? So this will be a solid line, for example, and then this would be a dotted line. It means that you don't see it. And then this one again will be a solid line. That will also be a solid line, if I can understand it. Okay, so this will give me this disc. A narrow cylinder is usually called a disc, yes? Anyway, or washer, yes? So what do you write for the volume of this cylinder or a disc? If you look at the formula sheet, the volume is pi r squared, yes, times height. But this will play the role of the height, which is this, and r is that. Yes, you can see that this parameter that I had from the beginning, h, will play the role of the height, and this distance will play the role of the radius, yes, of that cylinder. So the volume of this thin or whatever cylinder is that number there. Yes, is that okay? Okay, now let us go back to our original picture, and we want to discover the formula for the volume of revolution. Okay, so let me just do it as before. Okay. Now, I want you to learn this process yourself. You want to discover an integral formula for the quantity that you are interested in. The quantity is the volume of that object that you see here. So what do? You start trying to find not the whole volume, but a small amount of volume. Okay? And if you succeed to write something for this small volume, then instead of using sigma to add them up, you use integral to add them up to find the whole volume. So what you need to do is to concentrate on one very small volume that you can calculate. Okay? So what I will do, if you don't mind, let me take this narrow rectangle again. I hope that you understand that when I say rectangle, it is not exactly a rectangle. Let me draw it a little bit thicker. You can get a sense of it. Okay, a little bit thicker doesn't hurt. Then you realize that this is not exactly a rectangle because of this problem. Yes, that's a little bit curved, so that's not a rectangle. But anyway, that we can imagine that is a rectangle. The thickness is a small thickness. It means it's a very small variation in x, because that's an x. So that thickness, I call it dx. So let me write it on the board. So this thickness, I call it dx. Why not dy? Because of obvious reason. This is a small variation in x variable. And where is x? I consider this length from the origin to that very particular point to be x. Okay? Now my question for you is that, do you know what that height is? What is that? Not f of dx. F of? No, dx is the thickness. So if you, okay, might be, I am confusing you. So let me draw, I'd ask you about this height. So what is this height? This point is x, yes? So this point, this length becomes f of x, yes? But this is a very thin rectangle. We realize what happens for a rectangle, yes? If I find the volume. So can you tell me what should I write for the volume of the very thin cylinder generated after this rectangle is being rotated? So what happens? According to the formula for the volume of the cylinder, I have a pi, yes? And then I have radius squared. Can you see what will play the role of that cylinder? F of x. But that radius should be to power 2. So this means that my f of x should be raised to power 2. Yes? And then multiplied by the thickness h, which is played by dx. That's it. This is the volume of this very thin cylinder. But your goal is to find the whole volume. What do? Naturally, you start adding those volumes together. But how many of those volumes are there? Infinitely many, so sigma is not useful. What is useful? Integral. So I would write integral, and then I need to tell me, do you remember when you write sigma, you say I goes from somewhere to somewhere. So here you need to tell me where x is going from to where, okay? Where is it going from to where? A to B. Finished. But when I add, this is no longer dv because I am adding them up. So this becomes what? V. dv was the volume of the small part. Okay, when I start adding them up, it means that I am adding all these volumes together. So if I add all these volumes together, it becomes the volume of the object I'm looking for, and the right-hand side becomes this. And that's the formula that you have in the book. That's the formula for the volume. Yes? Volume of revolution. And then usually, because pi is a constant here, people don't put it inside the integral, they pull it outside, okay? So when you see the book, this is the formula that you see. This idea is extremely useful. If you have time, I will tell, because this is also part of your course, you need to understand where integral becomes relevant sometimes. But let us just write this and practice a little bit about this today. So the volume of revolution, I pull pi out, and this is usually the formula that you see in the books. And sometimes, because they are lazy, instead of f of x, they just write y. It's also good to know, because when you say f of x, you usually denote it by y, but then it becomes y squared dx from a to b. This formula is given to you in the formula sheet, but I want you to understand where is it coming from. Let us try to play some games now. For example, there are a lot of solids that you see the formulas in the formula sheet, but probably didn't know why. Let us do it one by one. For example, I don't know if this is the best example or not, but let me try to start with the volume of a sphere. Okay, so the volume of the sphere in the formula sheet is this. If I have a sphere of radius r, the volume, if you check the formula sheet, is this one. R is the radius. Okay, but let us see why. We want to prove it now, that this is indeed the volume. Okay, but let me be careful. Here, if I want to use that formula for the volume, do you remember I didn't start it from the solid object in the beginning. I had a 2D object that was my area. I rotated it about the x-axis. I generated the volume. That formula tells me the volume of that generated object. So if I give you a sphere, what should you imagine in your head? A sphere is the generated object. In order to use this formula, I need to go to 2D, to 2 dimensions, and imagine a curve so that when it is rotated about the x-axis, it generates the sphere that I am looking for its volume. And it's not hard. Yes? So, can you come up with an idea?
It should be a half circle.
Half a circle of, when you say half a circle, I expect you to tell me where the center is, and I expect you to tell me where what is the radius. Yes?
I don't think center matters.
Exactly.
Could be, it's a variable.
No, so I have this sphere, so let us draw this sphere for you. I have a fixed sphere with radius r. I want to find the volume of this sphere.
Then the radius is r.
There should be r. So the radius of the semicircle should also be r to generate this. But as you told me, it doesn't matter where the center is. Because if I take the center here, and this becomes r, and this becomes r, my picture is not very good, this should also be r, this is the semicircle. I hope that you understand that if I rotate it, it becomes that sphere. Okay? But as you told me, if I take not this one as the center, take this one as the center, and I do that, it will also generate this. This is important to understand that not all of them are mathematically, calculationally equivalent. If you can come up with all those calculations, the answer will be the same at the end. But one choice of the origin might make the calculation simpler. And I think it's a good idea to also understand the role of symmetry. So if I want to do it, it's working, but it is not very symmetric. What is the most natural symmetric choice of the center? The origin. Yes, because if I take the origin, what happens? And it is more symmetric, yes? So I would say that this is the best choice. If I rotate this curve from here to here, okay, if the radius length is r, what is the x-coordinate here? Minus r. What is the x-coordinate there? R, if my radius is r. And then you see symmetry happens. It is minus r, r. Working with minus r, r is easier than working with two completely different numbers. So now what I could motivate you, hopefully, is that everyone agrees that if I take this curve and rotate it about the x-axis, it will exactly generate the sphere that I'm looking for, finding its volume. Yes? Yes? Okay. So now the formula is here in front of me. I have to fill it up. Okay? To fill up the formula for the volume, what do I need? Pi is a constant. I need to fill up here. I need to fill up here. I need to fill up here to power 2, and dx is always there. So if I answer these three question marks, and if I can somehow calculate the integrals using the methods we have learned so far, then what I get is my volume. Yes? So I think these two question marks are extremely easy to answer. What are they? Minus r to r. Yes, because this is what I want. So very good. So what can I write for this question mark squared? So it means that this curve has an equation, yes? For example, let us say, if I draw this curve, based on your knowledge, you say, Bobak, this is y equals x squared. For example, yes? Or I don't know, if I draw this line, if this is equal, then you say that the equation is this. Now I have a curve here. I want you to tell me, what should I write for y? Yes?
Shouldn't it be r minus x squared?
Close, but not exactly. So my question is that, what should I write here? Because I need that. Why? Because I need to put it in there. So, yes?
Square root of minus r, or square root of r minus x squared.
Not r. Why do you say r? You also told r.
Yeah, or wait, are we confused?
R squared minus x squared. Yes? If you don't believe that, let us check. If I want to understand what is that relation, so what should I do? I pick a point there. Let us say that this length, this is x. I want to know y. When I ask you what is the relation, it means that you need to find the relation between x and y of every typical point on the curve. Okay, so I call this y, I call this length x, and I want to find the relation between x and y. But that's extremely simple because I can connect this, and this becomes the Pythagoras rule, yes? This radius is still r, and then x squared plus y squared is what? R squared. And the good news is that, by the way, do I need y? No. Look at the formula. What I need is y squared. Okay, and this is important. Just y squared is what? R squared minus x squared. But if you insist to continue and find y, what do you write? You have to write plus or minus this one. But which one is acceptable here? Because I am looking at this semicircle, which is above the x-axis, so the y should be positive. So if you insist to continue, you have the positive one because of that reason. But I don't need to continue like that. Why? Because I go back and see what I need. What do I need? I need a y squared. So that's in it. That's finished. So what should I write here? I write r squared minus x squared. Okay? Now we concentrate on calculating this integral. Whatever we get is the volume of the sphere. Let us check. Okay, let us see, because you had the exam just, you are fresh in this, so what do? If I want to calculate an integral, I need to ask myself, what is a primitive function of this function? Okay, but then I told you there is another rule for this dx. dx means x is your variable, because here you have two letters, English letters. In principle, any one of them could be variable. But which one is the real variable here? X. So r squared is what then? Is a constant. Okay? Because r is the radius of that sphere. Okay, so now if I want to find a primitive function, because this is a subtraction, I can do them separately. I can find the primitive function for r squared, I can find the primitive function for x squared and subtract them. This works for subtraction and addition. Yes? So tell me, so what I will do, I will continue that is equal to pi is pi. Okay, everyone, can you tell me a primitive function for r squared, having in mind that r squared is constant? Xr squared or r squared x, yes? So it becomes r squared x. It's like k, yes? What is the primitive function for k? Is kx. Here k is being played by r squared. Okay, minus, what is the primitive function for x squared? Very simple. X to the power of 3 divided by 3. Then I have to run it from minus r to r. Then I separate it into two parts, yes? Do you remember? So I just put pi. Instead of every appearance of x, I put r. So it becomes r squared r minus r cubed over 3. But r squared r is r cubed. So it becomes r cubed minus r cubed over 3. But this is simple. 1 minus a third becomes 2/3. So it becomes 2/3 pi r cubed. Agree? And I will do the same thing with the lower limit, but I have to put minus r this time. Minus r Yeah, you have to be careful not mess up the minus sign. So this becomes minus r cubed. But minus r to power 3, 3 is odd, it remains minus. There is another minus here, it becomes positive. So it becomes r cubed over 3. And then what happens here? Minus 1 plus a third becomes minus 2/3, yes? Yes? And then I go back to horizontal. I write the number above minus the number below. But then what happens? So 2/3 plus 2/3, 4/3 and pi r cubed. And that is your famous form. Yes?
Was it this way they proved spheres?
Yeah, I don't know, anciently no. Might be, I think the ancient way of doing it was the Cavalier principle. That's also a very interesting principle. So I think that Greek mathematician was able to find this because they knew about this from ancient times. We have this impression they were stupid, but probably they were much wiser than us because they have very primitive tools in their hand, you know. Yes. Okay. This is it. Okay, to test your understanding, let us do the same thing for the cone. It's a little bit harder. Okay, but I want you to understand, I give you a cone, you are not allowed to change my cone. You have to use this technique to calculate the cone that I give you. The cone that I give you is this one. By the way, before starting this, let me say something about here. My preference was not doing it like this. My preference was not going from minus r to r. I would prefer to rotate only this bit. But if I rotate this bit, what will happen? It gives me a hemisphere, not the whole sphere. Then by symmetry, I just multiplied by 2. So whenever you are doing these kinds of calculations, try to exploit the symmetry as much as you can because it will facilitate your calculations. For example, if I have done this one, what will change in my integral? Can you tell me? Let us say that I decide only take this part and rotate it. I know by symmetry my volume will be double of this number, okay? But if I do this, what will change in this integral?
The minus r will be 0.
0. It goes from 0 to r. It will lower the risk to mess up the minus signs here. Because if I run it from 0 to r, what happens? The r calculation is identical, but the 0 calculation is extremely simple because if I replace x with 0, everything vanishes. So then I go backward, write this one minus 0, which is 2/3 pi over 3, pi r cubed. Then I just know that I have to multiply by 2. It will give me back again 4 over 3. So in these kinds of arguments, try to exploit symmetry as much as possible. It will actually makes the calculation simpler. Okay, now my question for you is this, or at least you can guide me how to do it. I give you a cone. I fix the radius. You are not allowed to change my radius. The radius is r. And I fix you the height. By the way, if you go to higher level courses, this is called, what was the name? Perpendicular circular cone. Why do you think they emphasize on the perpendicular circular cone?
Because it's 90 degrees.
Yeah, first of all, this apex can be somewhere here. It would be a tilted cone. And the base could be an ellipse. So that will be elliptic cone. Okay? So here, of course, in your course, you just say it cone. But in principle, this can be tilted. So they say perpendicular to emphasize that this height is perpendicular to the plane in the center. And then they say it circular because then it means that this base is a circle. Okay? Okay. I want you to calculate the volume of this. You have it in the formula sheet. I don't know how many of you remember it. Do you remember? Okay. So 1 over 3 pi r squared h. Area of the base, pi r squared, multiplied by the height, 1/3 of it. That becomes the volume of this cone. Okay. This is harder than the previous problem because you need to imagine about a function so that when you rotate it about the x-axis, the generated volume is exactly this cone. Not exactly in this way of standing, might be the other way, or that doesn't matter. Okay? So can you imagine that? And you have to find it exactly. Yes?
Linear function.
Okay, but you have to fix it exactly. That's what I'm saying. You are right. So your understanding is correct. Because if I just draw a random line here, so first of all, if I just rotate this one, do you think it generates a cone? What does this generate? 2 cones, yes? So, okay, that's not a big problem because I can say that, okay, whatever it is generated here, I ignore that. Because that is under my control to run my x from where to where, okay? But the important is that let us limit ourselves for this right side. But this is, of course it becomes a cone, but not necessarily my cone. Yes, because if I rotate it about the x-axis, it will definitely generate a cone. But I don't want any cone. I want a cone whose radius is r and its height is h. So I have to do some adjustments. Okay, that's the whole point. I want you to understand that one, okay? So can you now fix it for me? So which line? Because you know the line is passing through the origin, you know the equation you are looking for should be of this type. Yes? Because you discovered that this is the line that I need. Any line passing through the origin has this form of equation, but still not all of them generate my cone, yes? I want to fine-tune the k in a way that when I rotate it, it exactly generates my cone. Okay, how do you answer that question? Okay, tell me, what should I choose for k? So that it, after being rotated, it generates exactly the cone that you see here on the picture.
It should be so that when
Exactly. Yes. Yes? Because you know that. Let us imagine, hypothetically, let us imagine that this is the responsible for generating my cone. If this is indeed, I don't know, let us say this is the other way around. If this is indeed my cone, then what happens? From here to here should be how much? This should be h. From here to here should be how much? It should be r. Yes? H is given to you. R is also given to you. What is not given to you is k. But you already know. You know that this equation, what is the equation? The equation is y is equal to kx. K is not known. But now, because of this, k is also known. Why? Because as Hafsha said, k should be somewhat, some number, so that when I put h in, it gives me r. Okay, so I put r for y. I ask myself what k is responsible, and I put h here. Do you agree? And then I find my k. What is my k? K is whatever r is divided by whatever h is. That's my k. And then I put it back into this equation. Then it becomes y equals to what? R over h k. R over h x. So that is exactly this is the line that exactly generates my cone. If I limit myself from where to where? From 0 to exactly h. Okay, now finally, can you tell me what is the volume? The volume is pi. I have to fix these 3 question marks. So what is the lowest question mark? 0. What is the one above? H. So this becomes pi integral from 0 to h, question mark to the power of 2. This is this expression to power 2, which is r squared, h squared, x squared dx. Yes or no? Okay. Now let us calculate this integral. This is the simple integral. What should I do with r squared, h squared? These are constants. So this becomes a multiplicative constant. So I don't care, I just pull it out. And then I ask myself, what is a primitive function for x squared? Extremely simple, a third x to the power of 3 over 3. And then I have to run it from 0 to h. And then 0 is simple, because when I put 0, everything is gone. So what I care is just putting h there. So what happens? It becomes pi r squared over h squared, h to the power of 3 divided by 3. And I hope that you agree with me, this 1/3, I can pull it and write it first. Then I write pi. Then I write my r squared, and h squared and h are canceled, 1h is left. And that's the formula for the volume of the cone. Yes. So that is actually the lesson. But most of the time, they don't ask you these types of questions. They just give you a curve and tell you that, okay, I want to rotate it above the x-axis. What will be the volume? This is just the formula, put things in. Okay, so of course you can generate fancy things, you know. I don't know. For example, if I ask you, yeah, I don't know, might be, by the way, I think engineers use these kinds of designs even for art sometimes. For example, let us say this function I have, y is equal to x squared, yes? Okay, and then let us concentrate between 1 and 3 here. And this one, okay, and you rotate this one. I don't know, you can imagine, I don't know. So can you imagine something like this happens, yes? I don't know if this is a nice shape or not. Might be you can make a table, or I don't know, might be you can make a vase or something. Yes? You want to find the volume of that. So it is extremely simple. So I cannot name it. There is no name for it. Yes? This is not one of those standard solid objects that we know about. But still, this is a solid object. I want to find the area. Extremely simple. It's E-level question. So what do? I write V is equal to pi integral from where to where? It was 1 here. 1 to 3. Be careful. This is a common mistake. People usually forget about raising to power 2. Yes? But this is the function itself. You have to raise it to power 2 by the formula of y squared. And then you calculate this integral. So it becomes pi integral from 1 to 3 x to the power of 4 dx. But this is a simple, so it becomes pi x to the power of 5 over 5 from 1 to 3. So this becomes pi 3 to the power of 5, which becomes 243 divided by 5 minus pi 1 over 5. So it becomes 242 pi over 5 cubic units. That's the volume of that object. Yes? So it is not hard at all. It's more or less the same thing, but you have to remember there is an extra pi in the formula, and the function itself should be squared and put inside the integral. Extremely important. Okay, before leaving that, we want to make it exactly like before. Now let us say that I have area between two curves and I want to rotate it, and I want to find the volume there. Yes? That's also simple. But still, I want you to understand the method I described. Yes? Okay. So here, if this is x and this is y, now let us say that let me draw it in a way that I can, yeah. So let us say that this is your function, y is equal to f of x, and let us say that you have this function. I don't know how to draw it, because it's hard to draw it by hand, but let us say this is y equals to g of x. And now I have this a here, and I have this b here, and this is the area. I want you to imagine it, because I cannot draw it. I want you to imagine, without changing the distances, you want to rotate this area about the x-axis, okay? And it will generate a volume, okay? So
Is it just the same as for areas?
yes, it's very similar to that, okay? Okay, one way, because I have drawn it in a way that you can understand what happens, I hope that you can imagine in your head, if I want to find this volume, what can you do? You can ignore the lower one and concentrate on the bigger area and rotate it. It generates a volume, but that is not the volume that I want, because it's also considering this part added to it. So what can I do now? I can do another one for this lower one, and then take it off from the previous one. That becomes the volume generated. So can you tell me what should I write now? For the bigger volume, I can write integral from a to b f of x squared dx with a pi outside. This is the volume if I don't see the one below. If I don't see the one above, I would write this gx to power 2 dx. I hope that you understand that the difference between them will be the volume that I am interested in. So that will be this. Okay, and then people usually write it in books like this. They factor a pi out, and you have two integrals subtracted in the same interval, so you can combine them into one single integral by subtracting the ones appearing in integrals, integrands, yes? And that is your, yes? So all those things that we considered for areas, you can also consider here. Except something that it is important to realize because of the second power. This is one way of deriving it. I don't like it that much. I want you to learn what I told you in the beginning using that idea. Okay, so let us just do it with that idea. This is very important. And when you go to university, usually this is very important. If I want to find this volume, what I do, I will do it like this. Again, let me just draw a thin rectangle here. Okay, so let me make it a little bit thicker. It becomes a little bit more real. Okay, not too much real. Okay, something like that. Okay, exactly as before. The thickness, I call it dx. Okay, and then here, this is x. So I want you to imagine what will happen. So let me ask you one question. If I give you this is called washer, by the way, I forgot to say, that is the one with the hollow inside is called washer. Because of those, I don't know, have you seen these plastic things that you put in the pipes to prevent leaking? That's called washer. Okay, so it's a disc but hollow inside. Yes. So let me ask you this question first. Let us say that I have a washer. Something like that. The inner radius is r, the little r. The outer radius is capital R. And let us say that I give you the height, the thickness. What is the volume of the washer? Yes. How can I calculate the volume of that, the meat of the disc? Yes. How can I calculate that? Yes?
Volume minus the smaller.
Yes. Yeah. The bigger volume, which is a cylinder, minus the volume inside. So the volume of the cylinder is what? If you remember, the formula is erased, but it is pi. The radius is squared times the height minus the same thing for the little r. So this becomes this one times h. Do you agree? Then I can factor pi and h out. It becomes r squared minus r squared. Yes? So if I ask you what is the volume of the washer, you will tell me the volume of the washer is pi multiplied by the difference of the squares of radii times the thickness. Yes? Okay. I want you to understand that if you ignore this part but keep the height the same, do you see that if I rotate only this part above the around the x-axis, it generates a washer? Yes or no? This is, I have to rely on your intuition. If you just take this part and rotate it about the x-axis, it will generate your washer. Okay? Pi is constant. I need to understand what is playing the role of this thickness here for that washer that I am generating. No, the thickness here. I'm just talking about this narrow one, not the whole one. The whole one is not a washer. It's a very strange object, yes? What? Dx. So the thickness will be dx. Yes? So the thickness will be dx. But now what I want to do, I want to know what is playing the role of capital R. I hope that you see that this rotated about will play the role of the bigger radius. And this one will play the role of the smaller radius. Yes? Okay. But now, if this is x, you know what this is. What is this? F of x. And if this is x, you also know what this is. G of x. So if I want to write the same story here, this is playing the role of your capital R. This is playing the role of your little r. Yes? And then you know the volume. So the volume is what? But I don't write the volume because this is the very small volume. I show it with dV. The small volume is equal to pi. Capital R is f of x squared. Minus little r is g of x squared. And then h is dx. If someone asks you, what did you find so far? I would say that I found a very small volume. Infinitely small, which is called infinitesimal. And then I'm looking for v. If I want to go from an infinitesimal to the finite number, I have to add them up, and that is integral. So this becomes v is equal to the integral of pi f of x to the power of 2 minus g of x to the power of 2 dx. But I should run x from where to where in my setup? From a to b, and that's exactly the formula I got above. Yes or no? Understandable. But now my question for you is that how do you think about this problem? I have this f of x here, but g of x is also here. And then I want to know, so this is also sensible, but I want to rotate above. This is meaningful again. Yes? But do you think what will be the formula? This is also important for me. Let us try to understand. About the washer, oh, I cleaned that. But what was the formula for the washer? It was pi, the outer radius squared minus the inner radius times the thickness. That was the formula for the washer. Okay, if I want to do the same thing here, so let us imagine, concentrate on this narrow part. I want to rotate. This is important, I want you to understand. Okay? Do you remember for the area, can you tell me what is the area between them? We had the math 4 lesson. Let us say here is A, here is B. So I wrote a formula for you, A to B, f of x minus g of x, d of x. And I don't know if you listened to the video or you just saw me telling you that. I told you that this formula is not sensitive where this area is. If everything is above, it works. If everything below, it works. If one part above, one part below, it works. So the formula for this area and the previous area and the area which is divided in two parts is still the same. Yes? For this volume, we realize everything above, what is the formula? This we have problems to understand. Forget about this momentarily. Now my question is that let us move everything below. What do you think will happen now? Do you think that the same formula, mean the upper one squared minus the lower one squared, will work again or not?
Surprised if they did it in the negative sign or minus sign.
Okay, let us try to see. This is a good question, I think. So let us try to understand. This thickness,
Oh no.
which is going to play the role of h, is dx. Yes? Let me consider from here to here x again. But from here to here is how much? Be careful about this point. What is from here to here? Okay, f of x is right, but the length, I want the radius. Radius cannot be negative. If you say f of x here is negative. So what is the length? The length is minus f of x. Yes, the length. I am talking about the length. And what is this length? Oops, minus is gone now. So minus f of x. The length is minus g of x. That's the only thing. But let us see what happens now. So the dv I am looking for is what? Is pi. And then what is the radius now? You see, the big radius is what? Minus g of x. So it becomes minus g of x squared. And then minus little r is minus f of x squared. And then I have h, which is dx. It flips the location, which was not the case for the area. You see, this one to power 2. Of course it is understandable. Yes? This is g of x to power 2 minus f of x to power 2. This is your dv. And of course, v becomes integral from a to b. Pi goes outside, and then I have g of x squared, yes, minus f of x squared. So this is not as simple as the previous case. In this case, always the curve above minus the curve below. But if I want to find the volume, it depends if this is completely located above or completely located below. And of course, for obvious reasons, yes? Because of course, if you want to rotate this, the one farther away from the axis will become the bigger volume minus the smaller volume. Yes?